Welcome to our last talk about these applications in harmonic motions. And this is the RLC circuit comes from electrical engineering. And surprisingly, it's very, very similar to what happens with springs. So I'm not an electrical engineer, so I apologize if my interpretation and explanation are a little bit simplified here, and also I won't spend too much time on this. So what's the deal here? We have a circuit, and let's draw the circuit in this way here. Okay, and there are four things actually in the circuit. So at each, oh no, I cannot do this, sorry, I have to. Okay, we'll start here. This is a battery. This means here is our source. We we add electricity to it. Okay, so this will be a function in t. So this will be eventually the forcing function. This will be where we add current. Okay, so we have always a plus and a minus sign, and we're gonna take the clockwise orientation here. So I'm going to put this here's a positive, let's do positive positive and negative negative, right? Let's do it this way. Okay, so then the next thing that we hit is the order in which we hit this is not important, but just for the picture here we have a resistance which apparently is denoted this way. Okay, so the resistor, and this is it has a constant called the resistance of that resistor. And again, so we have here negative, positive. There's a potential difference, and okay, the circuit goes on. The next thing, we have an induction coil. So and induction coils are, so this is an induction coil. And here the quantity, sorry, it's the inductance L that plays a role. And then finally we have a capacitor, okay, which apparently is something that looks like this. I wonder whether I think they made a mistake in the picture of the book, because the plus and minuses don't. I think they made a mistake, so I'm just going to stick with what I have, how I'm interpreting. So I'm sorry if I did get this wrong, but I think the book has the sign, the positions of the wrong. So the idea is that we go from negative to positive, right? So if there's a potential difference, that will cause the current to flow. So we're going to have a flow in this direction. Okay, so the way I depicted now. Okay. Oh, sorry, I forgot to write here. So this is the capacitor, and that has a constant C that we call the capacitance. And so this RLC refers exactly to these three numbers, R, L, and C. Okay, I don't know why they named it after that rather than RIKC, RIK, rather than RLC. I don't know. Okay, that's what it is called. Okay, so what is happening? So as we said, because there is a difference with potential difference from negative to positive, we will get a flow, and we will get a current. So I will be the current. Of course, everything depends on T here, but let me no longer write it. So I is the current. Now, what does that mean, current? I mean, the current itself, there is the current that is the flow of the electricity, and then there is the electricity at any point that is the charge. And how are current and charge related? Well, the current is the change of charge, right? A current means the word itself has this idea that there is electron or electricity going from one to another, right? There's a change of charge. So this means that I is Q prime. Why do we introduce current? Because that's what in mechanical engineering you're especially interested in the current. Okay, and this is slightly different than in the spring motion. So the current is actually a derivative. So if it would be if this would be motion, the derivative of position, if charge. So I'll make the comparison to what happens between a spring and this induction coil. This RLC circuit, and so the charge will be the primary function that we're going to charge to solve for. This corresponds to the y, which corresponds to position, and the derivative of that would be velocity, right? So current is kind of the velocity of charge. Okay, I'm going to write this between quotes, so it's the velocity of charge. Don't quote me on this, people, because they're going to crucify me, but just to have a picture of what's going on. Okay. Now, there is, what happens? There is so-called Kirchhoff's law. Law. It says the following. Well, what describes this? What is going on? Well, each of these three gadgets create a potential difference, and therefore create a voltage drop, right? Or voltage drop. I don't know. I guess because my minus and pluses are the wrong way, it's not, the drop is a bit weird. I don't know. I try to follow the description of the book, but they're definitely, the plus and minus in the picture is wrong, but I don't know how it has to be repaired. So I'm going to just go on with this one here. So it might be that it actually goes this way. I'm sorry about that. I really don't very versed in this thing. So with each of these three contribute, okay, in a voltage drop. And Kirchhoff's law says that the sum of the voltage drops must be equal to whatever the battery is providing you. So we have the voltage drop given to whether, so we have a voltage drop here, voltage drop VR, we have a VL and a VC, okay? So if we add these up, this is the same as whatever battery provides. If there is no battery, then it would be zero, okay? So what does that mean? So what are this VR? So for a resistor, it just, what does it do is, the voltage drop is proportional to the current. So it is just, and the proportional constant is the R of the resistance. So this was resistance, right? What about the capacitor? For the capacitor, Okay, let me do first, let me do it in order. The induction coil. What is that? For the induction coil, the voltage drop is proportional to the change in current. So it is proportional, the proportional constants being the L, what is it called? Inductance? No, L is inductance? Yeah, inductance. I don't know why they call this L. To me, it's because I is already taken for current. I don't know why current is I. I'm sorry, I don't know the details of this thing, the history of this thing. So, as I said, this is proportional to the change in current, and the proportional constant is what the L that we call inductance. Finally, what happens in a capacitor? In the capacitor, the voltage drop is proportional to the charge. Okay, so this is proportional to the charge Q. Now, for reasons that, again, historical reasons, one doesn't write C here, but 1 over C. So 1 over C, this is called the capacitance. Capacitance. These are just because, I mean, this is an old science, right? And everybody was developing it its own way, and they had introduced their own notions and notation. And sometimes it's a bit weird, right? Why not C times Q, but 1 over C? Okay. So that's what we have. Now, this doesn't look like a differential equation, but that is because we not really have used this fact yet. So if the I is the derivative of charge, then the derivative of current is the double derivative of charge, and now we see that this becomes a real differential equation. So it is R times I, which is Q prime, plus 1 over C Q, plus L times I prime, which is Q double prime, and that is equal to E. Let me not write the T here. Okay, so this is now a second order constant coefficients, and therefore linear differential equation in Q, in the charge. But as I said, electrical engineers are not interested in charge, they're interested in current. So while we normally solve a differential equation for Q, and that's it, we write down, okay, if in this case of the spring, we write down Y is, and we get the whole expression. What we need to do now is take the derivative of that to get actually what the current is. Okay, that's just the way things are in electrical engineering. Okay, but what this means nonetheless is we see again a second order differential equation with constant coefficients. And so if I would write it in the correct order, if you want, so if we first think of this as a free free oscillation, it's called free oscillation. So the current is oscillating, is running into that circuit, right? Free oscillation means that E is 0. That would be what we call the free movement in the case of our curve spring. We get this equation, right? So the E is 0. And so what does everything now correspond to? Okay, so compare this. So compare with the spring equation. That was my double prime plus cy prime plus km equals ky equals 0. Okay, so you see that the mass corresponds here to the L, which is the inductance. The resistance corresponds to the dampening. And 1 over C, so this is really a capital C, so I'm going to make my capital C's like that, because these are always capital letters, right, to make a distinction with my lowercase c of dampening. So 1 over C becomes then the spring constant, K, little k. Okay, so this is how you can, the book has tables with comparison between the two movements. So what can we now look at? Well, remember we talked about dampening, and we had under, critical, and over dampening. Okay. What do it corresponded to? Under corresponded to the discriminant is negative. This corresponded to discriminant equal to 0 and over discriminant bigger than 0, which means two complex roots of the critical equation, which of course, so the critical equation, the characteristic equation, let's write down the characteristic equation here for this guy would be LT squared plus RT plus 1 over C equals 0, right? That would be our characteristic equation, And if this has two complex roots, then we're in an underdamped situation. If this has a single root, that's a bit special case, that is the critical one, and this would be the overdamped. sorry, this corresponds to 2 real roots. Sorry, that's what I was writing here, 2 real roots. Okay, so let's do an example here. It's better perhaps to work on an example. And the idea is, it's nothing new. Once we realize that it's the same as before, well, we just solve these differential equations, right? And we reason the same way. Now, a lot of stuff of spring and harmonic motion I didn't discuss. I didn't discuss amplitudes and all that, and phase angle and all these things. But you can do this for this. The purpose is not to do a course in electrical engineering. The purpose here is to show that these are just differential equations and how we can solve them. So here's an example. There's another issue which I have really not very little knowledge about, is all the various units that these things are measured in. So I'm going to I will read them, but I'm going to ignore the units and just assume that everything is in the correct same system. So we have a current, and it's at the start we have 2 ampere. So currents are measured in ampere, flowing in an RLC circuit with a resistance of, so the resistance is 40 ohm, and the inductance is a half Henry. So these are the ohm and Henry are the units that we use here, but I'm going to ignore them. I'm just saying these units match. That's the only thing that I'm going to, and I don't think they're going to try to fool you anywhere. And so we do, and a capacitance, and here is 10 to the negative 5 farad. That's so, okay, if you want, I'll write it down once so that you know what these things are called. This is 40 ohm, a half Henry. These are just names of people that have worked on this, and this is farad. Honestly, I don't know where that last one comes from. Find the current flow in the circuit at t if the initial charge, so the initial charge was 1 coulomb. So another unit that we have not seen. So charge is in coulomb, and so the current is in ampere. They don't write it. Okay. Okay, so these are the units. Now let's set up the equation. That's more important, right? So our equation is a half t square plus 40t plus, well, 1 over c, so 10 to the minus 5th reciprocal, that's 10 to the 5th, right, which is 10,000, equals 0. So we were doing now first a free oscillation. Okay, I don't think I will do another one, but because it's the same thing, I just want to give one example here. So okay, we solve this now. I don't want a half in front of it, so I'm multiplying everything with 2. So this is the equation I get. Oh, sorry, no, it's not a half, it's 1/5, sorry. It's a 1/5 here. I copied the number wrong, so I have to write this 200 and this 50. Let me rewrite this. So I copied it wrong from the question. So it is t squared plus 2. No, t. Now I'm writing down the characteristic equation already. Let me first write down the differential equation. Right? Let's do things in the right way. So it's this equation that I'm writing down now. Okay. So this was 1/5 q double prime plus 40 q prime plus 10,000 q equals 0. So the characteristic equation is, but I'm going to already multiply also with 5. So that's t squared plus 5 times 200t plus 50,000 equals 0. Yup. So we need to find here what is t? T. Let me again use z. So sorry about this with all these variables, right? Z here and a z. So z squared and a z here. So z by the quadratic formula is equal to minus 200 plus or minus square root of 200 squared, that is 40,000, minus 4 times 50,000, that's 200,000, divided by 2. 40,000 minus 200,000. So we see here that our discriminant, let me write it up, what is discriminant here is 40,000 minus 200,000. It looks worse, but bad, but it's actually not so bad because it's 160,000, which is 400 squared. Which is yeah, that's right. Sorry, negative. So we know that we're going to have two complex solutions here, and so this would be there. This is the minus 200 plus or minus the square root of 160,000 is 400 I, because it's the square root of a negative number, divided by 2. So we get minus 100 plus or minus 200 I. These are our solutions. So what does this mean? That the homogeneous solution Q homogeneous, well, there's no homogeneous, sorry, I shouldn't write homogeneous here. Q is, it is a homogeneous equation, right? It's not a complementary. So Q is equal to, well, we remember this is the lambda, this is the omega, so that is A times e to the minus 100t cosine 200t plus b to the e minus 100t sine 200t. Okay? Okay, so that's how it looks like. Let's try to solve the problem that was with initial conditions here. If you hear this in the background, this is a big thunderstorm that is coming through here. That's don't get scared. All right. So what is going on here? The initial conditions. Did I say? Yeah, I said it right. There's no force. The initial charge was one capacity. Where was it? The initial charge was 1 coulomb. Okay. So charge Q. So T equals 0. Q was 1. And well, there was something else that they told us. I didn't forget to write it down. At T equals 0, the current has 2 amperes. So what is the current? That's I, right? It's 2, but that is the derivative of Q. Don't forget that current is the derivative of Q, and that was 2 amperes. So we get 2 there. Okay, so these are the initial conditions. So first of all, T equals 0, plug this in, and then we get 1 is equal to A plus B. Okay, and now we need Q prime, which is then, if you want the current. It's good to do this because we actually eventually this is what we want. Okay, so let's do the calculation. It's minus 100 A e to the minus 100 t cosine 200t. That's the derivative of the e function. Now we have to do the derivative of the cosine. That is also with a negative sign. And there's a 200 now coming out. 200a e to the minus 100t sine 200t. Okay, that's the derivative of the first term. Now the same with the b's here. We get minus 100b e to the minus 100t sine 200t minus, no, a plus now because the derivative of sine is just cosine, 200b 100t cosine 200t. Okay, so we plug in t equals 0 again, so it's the signs are gone, so we only look at the cosines. We get a minus 100a, and the other one is a plus 200b. Okay. And so, okay, what can we do? We can multiply this times 100 and add it to this one. Okay, So it was a gift that gives me 102, 100 plus 2. 100a minus 100a cancels. 100b plus 200b is 300b. So we see that b is 102 divided by 300, which is the same as 51 divided by 100. So it's 0.51 if you want. And a, well, a is then a is then 0.49, right? 0.49, because they have to add up to 1. Okay, so, or you can leave it as fractions if you want. Oh, sorry, I made a mistake. No. I'm sorry, guys, this is wrong, right? Do you see where the mistake is? Okay, I'm sorry, let's do this here. What is my mistake? My mistake is here. There's no b here, because the mistake is this one. This is a sign, so there's no b even here. That's the mistake, right? There's no b. So a is 1. Okay, that's there. A is 1, so this 2 is equal to minus 100 plus 200b. So that means 102 equals 200b. This means that b is equal to 102 divided by 200, which is 51 over 100. 51 over 100 is 0.51. And a is just 1. So our solution is, so what is our solution now? Okay, if we want to describe the current, I'm sorry, I'm baffled what the book writes here, differentiating these yields. Okay, right, so let's now write down what it is here. We can plug in a and b in here, because that's what we really want, or we can pull it back in here and then take derivative again. Now, I'm not a big fan of taking derivatives too many times, so I'm going to plug it in right in here. So I'm going to plug everything in here. A is 1, and let's leave this as 51 over 100. It's going to be, I don't want to write decimals here. So we get I is minus 100 e to the minus 100t cosine, well, the e to the minus 100t, that's everywhere there. So let's factor that out, sorry. I'm going to make, in this kind of things, you sometimes have to be a little bit smart to not have to write too much and actually get your calculations better. So e minus 100t comes out because that's every term has that in it. And then what we have a minus 100 times a, but a is 1, so minus 100, and with a cosine 200t. Then we have a minus 200 times 1 sine 200t. Then we have a minus 100 times 5100, that's minus 51 e, no, the e is gone, sine 200t, sorry, this is where I'm plugging this in, right? And here we have 200, so that would be minus 102, plus 102 cosine 200t. And now we can combine the cosines. So this is e to the minus 100t. We get minus 100 plus 100, so 2 times cosine 200t. And we get a minus 200 minus 51, so this is minus 251 sine 2t. And this is how the current, now we see that the current is not 200t, right? We see that the current is again a sine and a cosine, so what will happen is, as with an undamped, as an unforced spring, with dampening, because what's the dampening, right? Remember, the dampening comes from the resistance, right? Resistance corresponds to dampening. So there is dampening here. This means that the amplitude is getting smaller, and this means that we have this this periodic sine kind of behavior. So again, the picture is something like that. So we have e to the minus 100 and e. These are very extremely fast descending function. So this is a misleading picture. But and then the current, when we started, I guess at 0, right? So we would get something like that. Okay, so we have a dampening because of the resistance. So right, so if you want an undampened movement, then you have to remove your resistor. Okay, it's the resistor that dampens the movement. So if you want to see the correspondence with a spring, an undamped spring, then you have only the capacitor and the inductions. So you have an LC circuit that will be undamped. The resistor makes it dampens it. Okay, all right. And so you see that again. Eventually, in the limit, this there will be no current anymore. Okay, I guess that is something you want. I don't know. I don't know where you use these things for. So I'm sorry. I'm very ignorant in the application of this. But I just wanted to show you the math. Okay, I'm not going to do what happens when there is a force, when there is a battery, because it's the same thing. Okay, I might assign a homework problem like that. So